Hello, I'm Stylianos. I'm a physics teacher with ATS, and in this video we'll try to solve question 3 from the 2022 AP Physics C exam for electromagnetism. Now let's scroll quickly to question 3. As we scroll, we check the basic concepts that we need, the basic prefixes and units, the basic rules that are given, and a few tips for calculus and geometry. We can check the answers for part 1 and 2 that we did just before, and quickly to question 3, where we have a light bulb of resistance 10 ohms, that it is, we can see on the diagram, a rectangular loop with length and width that are given, and a wire underneath, a wire below the loop, and it is given that the wire has a variable current C minus dt, where the C is given. So basically the current is 10 minus 2t, so with time the value of the current decreases, and at some stage it will become 0, and then it will be reversed and it will increase to the opposite direction. And in what is the direction of the magnetic field that is produced by the induced current in the loop, as the current changes direction? Okay. Now, in any way, not only when the current changes direction, since the value of the current is given here, the current at the beginning it is to the right, and later when it changes direction it will become to the left. So by using the curved right hand rule, we need to find what is the direction of the magnetic field on top of the wire. So at the beginning the magnetic field is out of the page, out of the level of the screen, and when the current changes direction, the magnetic field is into the page of the screen. So here the wire produces a magnetic field. The value of the magnetic field at the start is out of the page, and later it is into the page. So the change of magnetic field is into the page. Now the loop opposes this change, so the loop opposes its delta B, so the magnetic field of the loop is opposite to that, so it is out of the page. So this is our answer, and in order to justify this, we need to mention that initially the wire produces a magnetic field, as we said, out of the page. Above it, produces actually I need to change the wording a little bit here, produces a magnetic field above it, out of the page. Later, the wire produces a magnetic field again above it, that it is into the page. So the change of magnetic field is into the page. And we need to mention that the loop opposes to that change of magnetic field. The loop opposes, so the magnetic field of the loop is the induced magnetic field. Actually, we need to mention this, the induced magnetic field by the loop will be opposite to the delta B, so it will be out of the page. And then we move on. We need to calculate the magnetic flux through the loop at the time equals 3 seconds. Now, the basic law that we'll use for magnetic flux is magnetic field multiplied by area multiplied by cosine of the angle between the normal and the loop. Now, in this case, we can consider that the angle is 90 degrees, so we don't really care about the cosine. And the area of the loop is supposed to be length times width. However, we need to be a little bit careful here. If the magnetic field is constant, we have the right, if the magnetic field is uniform, not constant, excuse me, if the magnetic field is uniform, we have the right to use this law. However, the magnetic field that it is produced by the wire changes with the distance, is decreasing with the distance away from it. If we remember, the magnetic field by a wire, it is mu0 times current divided by 2 pi times the distance away from it. So we have a small distance away from the wire and later a greater distance away from the wire. So the magnetic field is not uniform. If we could see, the magnetic field has a relatively big value close to the wire, smaller value away from the wire, and even smaller value more away from the wire. So we need to consider how this changes, how this affects the magnetic flux. And for this, because the value of the magnetic field is not constant with respect to the width, we'll not write this equation for the magnetic flux, but we will say that the magnetic flux is the summation of the magnetic field times the area, in other words, integration. So magnetic field multiplied by the area or multiplied by length times d width, but the width is the distance away from the wire, so it is dr. So we can say that the magnetic field is integration. The magnetic field is mu0 times current, so we need to play a little bit with this. Mu0, it is 4 pi times 10 to the power of negative 7 over 2 pi, the distance r is a variable, and we need to find the magnetic field when the current, when the time is 3 seconds, so the current is 10 minus 2 times 3. Actually, I will write it as a function of time because maybe later we will use this, but 2 times 3 is 6, 10 minus 6 is 4. This 4 and this 2 will cancel, so we'll have 2 times 4, so 8 times 10 to the power of negative 7. Also the pi and the pi cancels, and we have over r, and the length is 4 centimeters, so 0.04 multiplied by dr. Now, regarding the boundaries of this integration, the width is, the distance away from the wire is from 1 centimeter to 1 plus 2 centimeters, so from 1 centimeter to 3 centimeters, so from 0.01 to 0.03, so the phi is equal to 8 times 10 to the power of negative 7 times 0.04, integral from 0.01 to 0.03, 1 over r dr, and you will give me 2 minutes in order to try to calculate this integration. Actually, the integration will be a ln of 3 multiplied by the value 8 times 0.04 times 10 to the power of negative 7. So this brings approximately 3.5 times 10 to the power of negative 8 Weber. 3.5 times 10 to the power of negative 8 Weber. If you don't remember the value or the unit of the magnetic flux, we can say Tesla times meter to the power of 2 from this rule. I'm going to remove this. And we can move on to part C. And we need to find the current through the light bulb. when the time is 3 seconds. Now, we cannot find the current directly, but we need to mention Faraday's law, which states that the induced EMF is equal to minus number of turns, derivative of magnetic flux with respect to time. So the induced EMF, we only have one loop, so minus 1. Now the derivative of the magnetic flux, actually we need to produce the rule for the magnetic flux, and again we mentioned that the magnetic flux is integral from 0.01 to 0.03, mu 0, which is 4 pi times 10 to the power of negative 7, times the current, but the current now we'll write it as a function of time, so 10 minus 2t. Let me pause here and explain why I'm doing this. We mentioned that the induced EMF depends on the time, so somehow I need to produce a relationship with time. That's why I bring this in the magnetic flux, divided by 2 pi r, so 2 pi, and the r is the variable in the integration with dr. So the phi will be, I'm going to bring everything that is not important outside the integration, so 4 pi times 10 to the power of negative 7 times the bracket divided by 2 pi, and the only thing that stays in the integration is the 0.01 to 0.03 1 over r dr. This, we said that it is ln of 0.03 over 0.01, so ln of 3, and again the pi and the pi becomes cancelled, the 4 and the 2 brings a 2, so 2 times 10 to the power of negative 7 times ln of 3 multiplied by the bracket 10 minus 2t. So in order to find the induced EMF, we need to derive this for time. So we write somewhere this, that the phi is equal to 2 times 10 to the power of negative 7 times ln 3 times 10 minus 2t, and the derivative with respect to time is exactly the same thing, multiplied by negative 2. So it will be negative 4 times 10 to the power of negative 7 ln 3, and that's the value of the derivative, so minus 4 times 10 to the power of negative 7 times ln 3. So the induced EMF, give me a moment for this, 4 times ln of 3, it brings 4.4 times 10 to the power of negative 7 volts, and we need to find the current. The current is, the induced current is V over R, so 4.4 times 10 to the power of negative 7 divided by the resistance, which I believe it will be given somewhere, over 10. So the induced current is 4.4 times 10 to the power of negative 8 ampere. And we can move on to part D, where it is given that the group of students attempted to verify the experiment. However, the current is measured to be greater than what we found in part C. The real value of the current is greater than the value 4.4 times 10 to the power of negative 8. And how can we explain this error? How can we explain this discrepancy? Now, we need to remember that the induced EMF was minus number of turns, change of flux with respect to time. The basic, like in order to have greater current, we need somehow to increase the flux, so to increase the change or the rate of change of flux, how fast the magnetic flux is changing through the loop. Let's see the possibilities. The students did not account for the Earth's magnetic field. Now, obviously, if the students do not account for the Earth's magnetic field, the magnetic field of the Earth will add to the magnetic field of the wire, but the change of magnetic field will be the same because the magnetic field of the Earth is constant. So again, the magnetic field, the change of magnetic field will only be affected by the change of the magnetic field from the wire. So this doesn't explain why the rate of change of the magnetic flux is greater. Now the rectangular loop is tilted. Even if it is tilted, then this will decrease the magnetic flux. And if the magnetic flux decreases, then the rate of change again will not be affected, or if it is affected, will be decreased. This will not produce a greater current. The resistance of the light bulb is increased, and again the current is V over R, so more R will not bring more current. Actually, the opposite. More resistance will produce less induced current. The next possibility is that the long side of the rectangular loop is shorter, and again, if the side of the loop is shorter, this will decrease the magnetic flux. So again, since the magnetic flux decreases, the rate of change of the magnetic flux will be even less. So this will provide a smaller value for the induced current. So the only possibility that remains is that the current in the long wire changes at a faster rate, and this is the correct part, because if the current changes at a faster rate, if this current from the wire changes at a faster rate, then the magnetic field produced by the wire will change at a faster rate, and the change of magnetic flux through the loop will be, it will have a greater value. So we select this option, and we try to explain that the current of the wire, the change of current in the wire, the rate of change of current in the wire is actually responsible for the induced current, will affect, actually it will increase, not only will affect, it will increase the change, or a little bit better, the rate of change of the magnetic field, and more specifically of the magnetic flux. And according to Faraday's law, this will increase the induced EMF, and according to Ohm's law, V over R, more EMF will produce a greater value for the current. And I think this is our last part. Actually, no, we have one more part. Now we tilt the loop in this way, and we have the same rate of change of current, but we need to say something about the induced current, the new induced current, if it's going to be more, less, or the same like the induced current before. We found the induced current before. I think the value was, in part B, 4.4 times 10 to the power 98. So if necessary, we can apply the same calculations in order to find the value. However, this will take a little bit long, and we don't want that. So the reason why there is an induced current is a change of magnetic flux. And if you remember, the magnetic flux is the flow of magnetic field lines through the loop. So basically, we need to have an understanding if there will be more or less magnetic field lines that are crossing the loop right now. Now, the magnetic field lines will be a little bit less, because we said that the magnetic field is not uniform, like it decreases with the distance. So right now we see this value, this number of magnetic field lines. So you can see 1, 2, 3, 4, 5, 6, 7, 8 magnetic field lines. And try to imagine that the same distribution of the magnetic field lines, you bring it in the new diagram. So it will look like approximately like this. So right now, a smaller number of magnetic field lines is crossing this loop because the new geometry of the loop is different. Like the long side is here, so this decreases, this change of orientation decreases the value of magnetic field lines through the loop. So since we have fewer magnetic field lines, the rate of change of magnetic field will be smaller, and this will decrease the value of the current, of the induced current, and we'll try to explain with a few words. Now, the magnetic field by the wire, magnetic field by the wire decreases with distance. So the magnetic flux through the loop now is less because of the new geometry, and the delta phi over delta t is less than before, decreases, and this decreases the value of the current. Now, thank you for watching. Feel free to write your comments to write the comments on the video below. I hope you have productive studying for your exams, for all your subjects, and the most important of them all, which is physics. Thank you for watching. Have a good time.